For the final video in our series on chemical reactions, we're going to look at how to solve arguably the most challenging type of problem in the whole unit, that being how to complete a chemical reaction when you are only given either only the reactants or only the products. Now, we can do this first by figuring out what type of chemical reaction is happening, because if we remember what the general formulas of each type of chemical reaction are, it makes predicting what the products are to be much more straightforward. For example, if we take a look at the first example of reaction, we can see that elemental magnesium and oxygen are reacting with each other, and we can designate these as A reacting with B. Now, for those that remember their types of chemical reactions, you'll recognize that there is only one type of chemical reaction that involves singular elements reacting with each other, and that, of course, is the synthesis reaction, in which the two elements A and B join together in order to form a single compound as the product AB. And this, of course, would be magnesium oxide in this case. And we can check that we got our chemical formula correct by checking the charges of magnesium and oxygen. So magnesium has a charge of +2, and oxygen has a charge of -2. So we can see that the chemical formula works itself out, because +2 minus 2 is 0. So magnesium oxide with one atom each already has a neutral charge. So we have successfully constructed our skeleton equation here, and all that we have left to do is balance the chemical reaction. We're actually going to do this here because it's quite straightforward. We add a 2 in front of magnesium oxide to balance oxygen, because there's 2 oxygen in oxygen gas, and then all we do is add a 2 to elemental magnesium here. Now, for our next two examples, even though the chemical reactions are more complicated, we solve them in exactly the same way. So if we take a look at our second example here, we see that there are two ionic compounds, barium phosphate and sodium perchlorate, which we can designate as AB and CD. And again, this, if we recognize what type of chemical reaction matches this general formula, there is only one type of chemical reaction involving two ionic compounds that react together, and that, of course, is the double displacement reaction. And if we know that a double displacement is taking place, we know that the metal ions, or the cations rather, will switch places, and that will predict what the products are going to be. So if we take barium and sodium and switch places, so we can write barium here paired with perchlorate, and sodium switches places with barium, meaning that sodium will be paired with phosphate. And in order to get our correct skeleton equation, we can check the periodic table to confirm what the charges are. So barium has a charge of +2, and sodium as an alkali metal has a charge of +1. Perchlorate, which is a little tricky to find, has a charge of -1, and phosphate has a charge of -3. So all that we need to do is make sure that the positive and negative charge in each compound combines to 0. So if sodium has a charge of -1 and phosphate has a charge of -3, it's easy. We need 3 sodium, because +1 times 3 is +3, and +3 minus 3 from the phosphate is 0, so our chemical formula is correct. Likewise with barium chlorate, barium has a charge of +2, and chlorate has a charge of -1, so we see that we need 2 perchlorate ions, because +2 minus 2 is 0, and we have our skeleton equation. In the interest of time, we're not going to balance this or the reaction below to keep this video succinct, but you can balance this on your own following the strategies you learned in the previous video. Our final example of a reaction, discerning observers will see that our starting reactant here contains only carbon and hydrogen, meaning that this is organic. And if we burn an organic compound in the presence of oxygen gas, we know that we are going to have a combustion reaction. Now, because we're not given the products, we actually have a choice about whether we do a complete combustion or incomplete combustion. I'm going to keep it as a complete combustion to keep the product prediction relatively straightforward, because every complete combustion reaction involves the burning of an organic compound to produce carbon dioxide gas and water vapor. And once again, you can balance this on your own in order to keep this video succinct. Now, a variation on this type of problem involves converting written descriptions of chemical reactions into a balanced chemical equation, but once again, the steps remain the same. All that we need to do is read the description and figure out what type of reactants are reacting together. So here we have potassium metal, so solid potassium reacting with liquid bromine. And we remember that bromine is a diatomic compound like this. So yet again, we have another example of A plus B goes to AB. So because potassium and bromine are both singular elements, this would be another example of a synthesis reaction, in which case we would get potassium bromide. Now, in the interest of time, we remember that potassium is an alkali metal, meaning it has a charge of +1, and bromine is a halogen, meaning that it has a charge of -1, so 1K and 1Br gives us the correct balanced neutral chemical formula, and this is an easy one, so we can actually balance this reaction relatively straightforwardly and still have enough time to take a look at the next examples. We can see in our second example here, we have two ionic compounds, and as we saw in one of the previous examples, that gives us a hint of what type of reaction is going to occur. So here we have silver nitrate reacting with zinc chloride, and we can do a quick check of the periodic table to double check charges. We see that silver can only make a charge of +1, while zinc can only make a charge of -2. Chlorine has a charge of -1 as a halogen, and nitrate on our polyatomic ions table can only make a charge of -1. So silver has a charge of +1, nitrate has a charge of -1. This is 0, so our formula is correct. Zinc has a charge of +2, and chlorine has a charge of -1, meaning that we need 2 chlorines in order to get a charge of -2 to balance out zinc's positive charge. Now we can see that if silver nitrate is our AB and zinc chloride is our CD, this is going to be yet another double displacement reaction, and so we can predict what our products are going to be simply by taking the metals and switching them like so. So zinc is now paired with nitrate, and since we've already looked up the charges, we need 2 nitrate here because zinc has a charge of +2, and therefore nitrate's charge of -1, if we multiply that by 2, +2 minus 2 is 0, and then we can see that silver is now paired with chlorine, and because each of them have a charge of +1 and -1 respectively, we can see that our chemical formula is fine, and all that we need to do is balance this reaction. For our final unknown, we can see the word burned is kind of a hint about what type of chemical reaction is occurring, and oxygen gas is clearly spelled out here as one of the reactants, and we can see that our other reactant, a chemical called benzene, is only made of carbon and hydrogen, meaning that this is another clear example of a combustion reaction, and our description actually says that this is burned in enough oxygen for a complete reaction, meaning that we have yet another complete combustion reaction, so we can complete our skeleton equation by writing in carbon dioxide and water vapor. This concludes our video, the last video in this series. Now, if you follow the steps outlined in this video, that being determine the type of chemical reaction, determine the missing products or reactants in the chemical reaction by following the general formula, followed by balancing the reaction, you will see that even though these problems seem tricky at first, they are actually relatively straightforward and can be solved in the same way each. So to test your understanding of how to complete incomplete chemical reactions, you can take a look at the practice problems below, both completing missing chemical equations, and then the more challenging variety where you can decode the written descriptions of reactants and then figure out the products again using the same steps.